Hello, everyone. Thank you so much for joining us today. This event is a part of the ZK month that is being hosted by the Phoenix Guild. We are a community that aims at getting more diverse builders into the Web3 space, and we do it majorly through education and mentorship. Our today's speaker is Minnie. Minnie has a lot of accolades to her. Majorly, she has also done workshop with us earlier with Women Who Code. And she works with Dell Technologies right now in the domain of embedded system security. She has experience in defense, semiconductors, consumer electronics, substation automation, and industrial measurements. And her specialization is in cybersecurity, embedded systems, and system architecture. So she is currently also pursuing her PhD in embedded security. And one of the things that I want to say, add to her already amazing profile, is that Minnie is someone who's very, very approachable. And the idea of doing this entire series this month is to make sure that to bring everyone a step closer to technology space, to bring everyone a step closer to the zero knowledge space. And a part of this involves also learning a bit more about cryptography. So if you have any questions also later on, which could be basic cryptography questions and things like that, you can share it with me, and I'll also, like, I can share it with Minnie if it is something complex that I can't decode. But she's extremely approachable, so you can ask any question that you have in today's session as well. And I'm really super glad to be able to have her as one of the speakers in our session. This entire series of session, we are calling it the ZK month. And what you will learn in ZK month is a lot about cryptography, a refresher of various cryptography concepts. You will learn about an introduction to zero knowledge proofs, how they work. We'll look into, we'll deep dive into two specific zero knowledge proof based protocols. One is SNARKs, and another one is STARK. So SNARKs is succinct non-interactive arguments of knowledge, and STARKs is scalable transparent arguments of knowledge. These are the two most popular algorithms in the zero knowledge proof space, where you can see a lot of innovation, lot of things happening in this space. And then we'll also look at the different protocols that are working in the zero knowledge space, and what are the use cases of these protocols. A quick note about the Phoenix Guild. The Phoenix Guild was started early in 2022. Our community is mainly focused on providing things like education and mentorship through workshops, boot camps, creating inclusive events, and making sure that we are able to invite more women, more non-binary folks, more people from tier 2, tier 3 cities to come and join these events, learn, and then, be able to build their careers. We have regional hubs across the globe. So we have about 13 cities in which we are actively doing in-person events, as well as we have a chapter in Malaysia, and we are setting up a few chapters across Eurasia as we speak. And then we have opportunities that we offer to you. Opportunities come in different formats. One is definitely learning and getting connected to notable speakers. Second is we have job postings that you can see on your local community groups. And we have hackathons that we run, where you can participate and basically, build a company if you have that entrepreneurship spirit. Our mission and vision is to onboard the next million diverse builders in Web3. And we want to see a lot of people, a lot of these diverse folks represented in leadership positions in different companies across the board. These are some of the partners that we have worked with. And if you want to join our community, we have a global community which is on Telegram. And then we have Twitter that you can follow for updates and news and things like that. Thank you so much again for joining today. And as you go through the sessions, I hope you make sure to keep on incrementally, adding to your knowledge packet, and make sure to ask a lot of questions, especially in all of these sessions, because we are a small number of people and we are getting a very private space to interact with very knowledgeable speakers. So make sure that you can make the most of this time. That's pretty much me. Now on to you, Minnie. You can share your screen.
Thank you.
And we can get going.
The screen is there with you?
Yes, we can see the screen. Thank you.
Okay, thank you. And Gyan Lashmi, thanks for inviting me. Like for the audience, like we were in contact for quite some time, probably around 2019, 2020 itself, I think.
Yes.
Quite passive, but at the same time, we know that, okay, when needed, okay, you are there, kind of. Not very actively into contact, and we were speakers for each other for some time, one or two occasions before. And I was quite pleased with the remark about approachability.
Yes, definitely.
Yeah, I appreciate that remark as well as I appreciate that nature also, whether it is in me or in someone else. So that said, she has already told lots about me, so not adding to that. And if you are interested in more details, you can look up my LinkedIn profile. I didn't put it here, but you can look up Mini TG Dell Technologies. You will see in the LinkedIn. I have put some recordings from some of my previous sessions in public space. A YouTube playlist is there. If you are interested in topics of my interest, you can have a look. Most of them not into this kind of blockchain kind of technology space, but more into embedded system security, hardware security, closed hardware security, basis of cryptography, those kind of topics you can see there. They are quite interesting. So, like it will give you a different perspective of how can we use hardware into building security in all these cases, because all what we talk ultimately we need an underlying hardware to execute. So software alone will not reach there. So that kind of sessions, if you are interested, then you are free to have a look at there. And then let us start today. Cryptography basics. I don't intend to get into too much details of all the complicated functions, but the very fundamentals which you will need to know so that you can pick up anything and learn. See, that was the intention of putting it. It's not like this session will teach you everything, but it will give you the concepts clarity so that anything that you want to read, if you read anything or if you try to play around with some packages or software, instead of getting overwhelmed, okay, you should be able to relate that, okay, this is what we were trying to do and this is what is happening. So that is the intent of the session. And we will cover two concepts here, one hash functions and one is elliptical cryptography. There are so many other topics which we don't intend to cover today. One is due to time and also too many topics will confuse you. So these two would be the good collection which would be contributing to all these kind of zero knowledge and all that which she is talking about. I don't know those protocols and all. I'm primarily a cryptography and embedded system person. But feel free to ask anything anytime during the session. Like don't get confused and then not able to follow. If you're confused, stop me and ask any question. And let us now start. So when we talk about all these cryptographic primitives, uh, irrespective of what we are talking, whether it is digital certificates, whether it is about encryption, decryption, TLS, or even all what you are using in this underlying hash-based structures like your Merkle trees and all that. Ultimately, all these are built on three underlying fundamental items, which are one is hash function, another is symmetric encryption, and another is asymmetric encryption. Once you get hold of these three topics, almost all, I don't say all, but almost all of the topics that you will come across in this space is castles built on top of these foundational elements of hash function, symmetric and asymmetric encryption. And we will cover these two, hash function and asymmetric encryption. Symmetric, it is for some other time. When I say hash function, I am referring to things like once broken MD5, once broken SHA1, and then the SHA2 category or family of algorithms, or SHA3 family of algorithms. That's what we are talking in these hash functions. Like you will commonly hear terms like SHA256, SHA256, all those kind of terms. That's what we will cover here. And symmetric encryption, which we don't cover here. This is used for bulk data encryption. If you have to encrypt large volume of data, that because that is efficient, you can compute faster. That's a kind of work that happens in the, keep my chart open. What is embedded system about? Embedded system is they are typically resource constrained. Like if you heard about IoT and all that, your small light bulb compute, or it could also be mission critical system, which are very high hard real-time system. Like my personal exposure to embedded system, the first one was with a military fire control system. So the hardware itself contains that firmware. That's what you call as an embedded system. Like say if you look at a PC laptop, probably you can call the boot or maybe the board, bring up the board support packages, all those are embedded system. or things which you see, the washing machine, the control firmware that which is there in that, you could call as an embedded system. Or if you are talking of electrical controls, grid, your substation automation, all those also could be embedded system. So that like, which is not like a standalone application like Windows operating system. Embedded system also has an operating system typically, because you need to schedule and do all that. The timing and resource constraint nature, very critical hard real-time timing constraints and requirement, and resource constraint nature with respect to memory and low compute capacity. Those are typical characteristics that you will, and they'll be typically interacting with some real life field objects. And symmetric encryption, that is our AES kind of item, which once again I'm not covering today. And asymmetric encryption, the two most popular encryption schemes we are talking about is RSA encryption and ECC encryption. These are the two algorithms for the asymmetric space. In that RSA, once again, I'm not covering today. This one I'm not covering today. This ECC we will cover today. Okay. So that is the topic for our interest for the day. For the first half of the time, we will try to cover hash function, and in the second half, we'll try to go to the asymmetric encryption. I'm going slow with the assumption that I don't assume prior knowledge, so I'm just going slow. If you think that it is too slow, let me know. Okay, hash function. What is the purpose of hash function? They are one-way function. They are a representation of the input that you have in hand. It's not the input itself, but a representation of what that input is. So how that works is, you have a hash function. It can take any length input, arbitrary length input, anything non-zero, even if it is a 1 byte, to a large, huge volume file, anything you can take, and then to any length, to up to n, and then you can feed it into the hash function, and the hash function will give you a fixed length output. That is a very basic primitive of hash function. So there are certain properties. So say, let us call it a SHA256. You take any length input, give it to it. It's actually a cranking. You crank through all the input, you churn over, crank over it, and ultimately you come to a fixed length. Okay. And the fixed length, based on that length only, we keep telling this, which is, of course, there is an underlying algorithm. When you say SHA256, we are talking of 256 bits of this output, or you are talking about 512 bits of this output. That is where we talk about AES is the algorithm that is used there. And there are multiple families of algorithms. SHA-1 is one family, which is not a currently in use algorithm because it is a broken algorithm. You can try to go to the website called Shattered, where you could enter some kind of any input, and they will be able to break it and give you other inputs, which will give you the same hash functions. Okay. So Shattered is one. Which, just for playing around, you can go there and see how this SHA-1 is broken. Currently in use are the SHA-2 family of algorithms and SHA-3 family of algorithms. Okay, shattered.in. Yeah. So SHA-3 family of algorithms, these are the ones in use currently. SHA-3, the adoption is not so much. SHA-2 is very commonly adopted. 256, 512, all that are, and various companies and various organizations have their own baseline algorithm, nothing below that. Such a kind of baselines are put based on various parameters, the compute capacity of the device, how risky it is, and where it is kept. Considering all that, it is people select what is algorithm that to be used. So this is a basic concept of hash function. So you get an input, and then there are certain properties that we need to look at for a hash function. They are one-way function. One-way means you can only go and compute this way. See, if you are given the output, you cannot compute any function. When you take, you have a y is equal to f of x. Knowing y, you cannot compute x. That's what you say, that it is one-way function. And then you have other properties. Only when these properties are satisfied, you call it as a good hash function. That is where all these prior ones are getting broken. And if you are interested, I have put some references further. The NIST documents which talk about what is the strength, how do you call that it is good, the further mathematical details and analysis, you can look at those. I put them in the reference, you can look. One way is you only compute one way. And there is something called a first pre-image resistance. This is our next property that we are talking. First pre-image resistance is, say if you have a function called y is equal to f of x, y is what you call as your image, any function, and then x is what you call as a pre-image. Means you had a pre-image of x, and from that pre-image you are computing this image y. That's the concept. Okay. If you look at those terms, first pre-image resistance means if you have a hash function, given a value which is here, given a value of h, you should not be able to compute any kind of a data that is a message which will give you the same hash value. So if you get a hash value, you cannot go and find out any input that will give you that hash value. That is where you call it as a first pre-image resistance. That means you cannot compute any x which will give you the y. First, when you say one way, it means that you cannot go back. Say, let us assume worst case condition. Say x1, x2, x3, all of them will give you the same y as your hash function. And if you know y, the h value, you should not be able to compute any of the hash value, any of the original input which gives you this output. That is what you call as first pre-image resistance. And then the second property is second pre-image resistance. Let me clear up and get some space. Okay, second pre-image resistance means you already have a message known to you and you already know what is the hash value of it. Given a combination of a message and a hash value, you should not be able to compute another message which will give you the same hash value. Okay, so this should not be possible. That is when you call it as a second pre-image resistance. First pre-image resistance, given an h value, you should not be able to compute any kind of input that will give you that same h value. That means you may be going and computing the original input which gave you the same output, or you can it gives space for breaking the integrity. You are giving another message and then you tell that I got the same hash value. Here it is not possible to, in the second pre-image resistance, it's not possible to compute another message which will give you same hash. That's the second pre-image resistance. There is subtle difference. Like we originally only had a h value. So in the second case, we have a message and an h value. You should not be able to compute anything else. Okay, like how it comes into picture, we will see when we look at the signatures and all that. And the third property is collision resistance. Collision resistance is when you are computing, if you have messages, say M1, M2, M3 kind of messages, it should not collide into the same hash function. So as a property, you should not create same y value or h value. For multiple messages, you should not get the same. So that guarantees uniqueness. That is where you call it as a collision resistance. And then we call the last one as an avalanche effect. Avalanche effect means if you have an input, say a message, and then you get a hash value, any small change in the input, even if it is a one bit change in the input, they should not be uniformly distributed or any kind of, the change should be large enough in the hash value output. So that is what you call as an avalanche effect. Any small change should create large effect onto your output. It should not be that you change small value here and the output also changed only small little bit. Or you changed, say, something here, the output changed to something here. So you should not have patterns of that kind of input that is coming in. So the algorithm of hash function should safeguard you with all these properties. Small change should create large output. And then one thing which I did not write here, these hash functions, they also have a puzzle friendly nature. The puzzle friendly nature is like if you are looking at some kind of a Bitcoin mining kind of examples. The process of mining is you will be given some constraint and then you will be given some hash value and then so many bits can be zeros, so many areas can be zero, some constraint is given, and then you are asked to find out an input that will give you this hash value. That is the process of mining. So in that process, you should not be able to compute that very easily with a mathematical logic. You have to spend that amount of effort. Then only you can compute that. That is what the puzzle friendly properties. See, with all these property, you will get these hash functions are puzzle friendly by nature. Okay, do you have any questions or shall we go forward?
I have one question.
Yeah.
So, is it required that a hash function will satisfy all these functions or a combination of these functions?
No, it has to satisfy all of this. Then only you call it as a good hash function.
Okay.
Because if you are able to break any one of them, you are typically able to break most of them.
Okay. Because I read like few protocols in the zero knowledge space, they rely on certain properties of the hash functions, like the star protocol and the mathematics behind it relies on the property that hash functions are collision resistant. So it
Yes.
uses that property to derive
See, the
some.
thing is, okay, you said collision resistance, but let us assume, take the case of pre-merge resistance. Okay, first pre-merge resistance. You have a data and you have a hash. You are able to break the system. You lose the security if you don't have it. So if you are looking at a digital signature, for example, you get a data, you compute the hash and you encrypt it with your the private key and you get your signature.
Got
Okay,
it.
you lose the security.
Got
The
it.
security of that signature is lost if you don't have that property.
Okay. Got it.
Okay, second pre-image resistance means I can replace any other data D2 and then claim that this is what you have, right? Integrity can be broken.
Yeah. Yeah. Okay.
So if you have to call something as, these are security properties.
Got it.
There
Okay.
may be protocols which are making use of certain functions, certain properties.
Okay.
Like say, for example, the mining process, it is making use of the puzzle friendly nature.
Got it.
Okay, puzzle friendly nature is not really, it's an outcome. It's not really a demand that by like a hash function has to be puzzle friendly nature for to be a good secure hash function.
Okay.
These
Yeah,
properties
it's a
will
result of
guarantee
all of these
security.
properties. Ah, okay.
Yeah,
Okay.
these
Yeah.
are security properties.
Got it. Okay. Yeah. Thanks, Nidhi.
Anything more, or we'll continue?
We can continue. I didn't see the
Yes.
chat if there are any questions.
No, there is nothing there. It's
Yeah,
okay.
okay. So we can continue.
Okay, these are kind of little bit more explanation into the same. Okay, first pre-image resistance. Let us look at a summary. First pre-image means you have only one input. See, you have one h of y is equal to a hash value. You should be infeasible to compute y, which will give you then h. Second pre-image resistance, it should be infeasible given for any given block. It is infeasible to compute another y such that a hash of x is the same as hash of y. Like I have one data, I have a hash value, I can come with another data which will give you the same hash value. That should not happen. And then collision resistance is okay, you should not compute pairs of data such that both of them give you same output, same hash values. These are the basic properties. Like from your question, what I understood is certain whatever I have put on screen, they are security properties. But to build up castles on top of this, you may be making use of certain items.
Yeah, yeah. They make use of some of these properties to make sure that they can derive some assumptions. That
Yeah.
they make an assumption that this hash function will be collision resistant. So we can take that property,
Build
make sure to
something on
put
top of
something on
that.
top of this. Yeah, yeah. That's how it is. I got it.
Okay, these are the algorithms that we are talking about. SHA256, SHA386, SHA512. These are the kind of algorithm. I just put some samples. Okay. These are very commonly used functions which are today many people use. And there is a SHA3 family of algorithms which you can look up, but like it is getting adopted kind of a state right now. And some documents I had put, let me look at them so that I could show you right away. I have some documents which I had opened and kept with the intention of showing you.
There is a question, Mini.
Yes,
What
yes.
do these numbers stand for?
Oh, this numbers, this is the length of the output. See, you have your data and then you apply your hash function and then you get an h value, which is the hash. This is the length in bits of the output that you will get. We told, right, the output is always fixed length. Any amount of input you give, you crank over it and you come out. It's actually compression functions. Look at them as a compression function. Okay, these hash functions have a compression nature. So you compress them into reach to a fixed length output, and these numbers are the length in bits of the output that you are creating. there is a document which talks from NIST on using secure hash functions, like the best practices for using hash functions. It's there in the reference. Let us come to that. I did not open it and keep it. Now I may have to again go and load it. So let's keep it aside. Okay. So that's the document I'm referring. It's there. You can, they talk about which algorithm to use, what is the strength, what is the, all these properties when you call they have quantified all these image resistance and all that. We'll come to it. Okay, now let us look at some of those constructions we can do with this kind of hash functions. Okay, this is the very primary hash function property that we told. You can use them in multiple manner. Okay, this is where it becomes interesting. So you can form a chain by using hash functions. Okay, because they are one-way functions, which we understood already. And then using the one-way function, you can create higher level data structures by making use of the hash functions. So that is where many kind of, see what we are seeing here. Like if you are looking at a trusted platform module, they have something that you call as a PCR. PCR values are built using this. So this is one linear way of doing. What you do is you take a data and then you compute a hash function. You will start from somewhere. Okay. Initially, you may give some D0 as a initialization vector or something because you don't have a hash value in hand already. So you just use some initialization vector for starting. And then what you can do is you take your data and then you compute a hash and then you got an H0. Where if you really want to add more data to it, you add more data and it's actually concatenation. Okay. You take your data, this data and the input hash value. So you take your H0, concatenate with your D1, and on that you compute your hash function. Okay. This is what the concept of linearly chaining. So by chaining like this, you can create higher structures. So you add more data into it. You put one more data you got, but you want a single hash value to represent everything together. That's the purpose of this. Okay. So linearly you take the previous hash value. Once again, you append your original data, compute hash function, you get an H1. And then you take this H1 in hand, and then this the H1, and then take the next data. You keep on going like this, and then you get, and finally you get an Hn plus 1. So what happens is this Hn plus 1 is indirectly a representative hash function, which shows uniqueness of all the data that you had in hand all the while. It's not like one data you have. From the previous explanation, you must have understood that the hash value is a representation of the input data. So here, the last hash value is a representation of all the input data that you already had in hand, even though this data comes one by one. Any real life application where we use this linear hash chaining, that's what I told. One is the TPM, Trusted Platform Module, if you're aware of. They have something called as a PCR values, like say in your, that is to guarantee. I'm giving an example from my own familiar world of boot integrity. If you want to do a boot integrity, you know that when a system boots, you will have your first bootloader will be there, like a Linux kind of a place, if you think. Then you have your operating system, maybe there would be some BSPs in between. Then you have your applications, all that. So if you really want to guarantee the boot process integrity, you can compute a hash. When you first load the module, you compute a hash. Then next you load the module, you concatenate that data also and again compute the hash. Like that, you can keep hashing again and again on top of it. That's what is done in the TPM PCR value. Okay, so if you do this, the boot process integrity can be verified. Getting at the one value, you know that, okay, if this application for this specific version, this is the expected hash value. For this another application, the very specific version, that is a hash value. By looking at a single hash function, and ultimately, you can make out that all the modules are integrity protected instead of one value. So that is what you are able to do with this kind of linear chaining. Other example, if you want to see, I had put something in my slide notes. Let me have a look. You can use them for this OTP generation. S key. You can look at something called S key. There is an RFC for it. Okay. S key generation, OTP generation. If you compute all this, you can keep giving this OTPs one by one. Say first you give this one as your OTP. Like in that OTP generation, you don't use this data. Okay, you just take this. Clear the board. Like since you asked for some more example, you don't use the data. Forget about the data. You take all these values one by one. You ask somebody, okay, give me an OTP. You create some kind of a seed value, and then at the end of that you compute one hash one h0 h1 h2 all that. You give these as OTP values to someone. Say if you are able to execute something n times, and for every time you need to give one OTP. These are called S keys. You can look at it. S key as an OTP generation mechanism. If you have H0, H1, H2, you give them as OTP 1, 2, 3, 4 like that, and you start using it in the reverse order. Ultimately, after generating all these OTPs and sharing with the receiving person who will ultimately use this OTP, you keep only this HN plus 1. Okay. And up to this HN is given as OTPs. All these 1, 2, 3, 4 and HN are OTP. So if somebody is able to give you N as an OTP, and the beauty of that is after you shared it with someone in a secure manner out of band distribution mechanism, you don't keep even the seed value. You don't have to keep anything. So you don't have a space for security compromise because you have no value in hand which can derive this this value of HN plus 1. Not even the one who generated and gave it, because you are only holding this HN plus 1. So with this OTP generation, once you get this OTP, you compute the hash function and you see whether you are getting it. If it is fine, okay, this OTP is fine, I accept it. And whatever OTP you received, this you keep it as your new reference value. And next time you will get the previous one. You compute the hash value, you get it, and then if it matches, okay, the OTP is fine, and then you change the value to the whatever you received. So like that, you can use a series of n OTPs. That is another method. Okay. So all these are, there are various fine use cases which you can use for use with this kind of linear chaining of hash values. Okay. And then let us look at, there was something in the chat, what that is. S key. Yeah, this is the one which I was referring to, Lakshmi, the S key mechanism. Another use case is your typical Merkle tree that we are talking about, the tree structures. That is okay. Trees, these are trees created by me just for some interest. I put it there. Even the tree behind me is also created by me. I think you know that, okay, I have an interest into these images, fractals and all that. That's something different, a complex number thingy that is for fractal image creation. So just for fun, I think I keep using that. And what you are seeing there is, they are called the L systems or Lindenmayer system, just for fun. Trees are supposed to be top, up, down and all that, but then our Merkle trees became ulta, okay, upside down. The world became upside down. I'm standing and looking up. Okay, so these are very commonly used other structural creation using hash function, the Merkle trees. If you are into that blockchain basics, if you like, you will further progress, and if you get there, that's actually a hash tree. So what you do is you take your hash 0 and hash 1, you have underlying data further down. Okay, you take your hash 0, hash 1 and combine them together, concatenate, and then you compute a new hash value. Here similarly, you take 2 and 3, and then you compute another, concatenate and create another hash value. And in a similar manner, you create these binary trees, and then you go up to the root. Okay, so what happens is, if you're this root hash, the linear, it's an optimization of your linear structure, what we told before. Linear, linear data structures have higher complexity, whereas tree structures have better time complexity. So you get a computational efficiency by creating these kind of tree structures. So what you are ultimately getting is, you have a single root hash, which is a representation of the entire tree. If any node in the tree changes, you will get a different hash value. See, that is the purpose here. Okay. And then what you need to do, if at all any node changes, say if this node changes, then you will have to transfer not only this node hash value, you have to transfer all the hash values that get built into it. Say you have this one changed, and if somebody has to verify, you will also need to have in hand hash 1, then only you can compute this hash 0, 1. Similarly, the neighbor node, the sibling nodes also you need to give. And if you are asking some example, one is the Merkle trees which are used in your the blockchain space. And with the new changes that we are seeing is, if you look at those post-quantum cryptography, there are certain hash-based signature schemes. Okay, so some of the signature schemes are based on this kind of Merkle tree kind of hash signature scheme. There also, this is like you create say a series of signing keys and you keep using one at a time. That's a function. That's the way this hash-based signature scheme works. So they are another use of that. And if you are looking at other use case, say certificate transparency list, that is another use case which you can think of where it is used. Certificate transparencies. That website is very nice. Certificate transparency website is good. You can have a look at that. How these hash trees are getting used. And these are some of the structural constructs that we can do using these hash functions. And if you are talking of, till now I only talked about hash value itself, but then if you are talking of data, then you have these kind of transactions. Okay, like if you are talking about this blockchain kind of item, data or the transactions that you are talking, you take this data, this is your data, and first you compute a hash on the data and you get H0, and then further you build up this tree further, and then you reach to the root hash. Any change that happens anywhere further down in any node, your hash value changes. So this root, you can use it for integrity protection. Okay. That is where I come to. Then something which I like to also cover is about the construction, which I'm not getting into. It will be quite a bit involved to explain the construction. That is why I'm not putting it here. I would like you to go offline and then look at some kind of a textbook like Cryptography and Network Security by William Stallings or something. How the hash function works, how those compression function works. Because how they are working is, it's just due to time. Maybe you need one whole session just to explain this construction. So there are various rounds that happen. So you take some kind of initialization vector and you take your entire data and you break it into blocks. After you break it to blocks, you pass them through a construction mechanism. Okay. There are various constructions like Merkle-Darmstadt constructions and all that, which will tell you about how this construction works. And then you do rounds and rounds of construction till you ultimately reach to a point that you got that fixed length output. And if you have any kind of data which is not fitting into the specific block size that is expected, for that block size you pad it with the padding is also specified in the algorithm. So you pad it and extend it and make it a full block length, and then you go through these rounds, and in those rounds there are some constants that are involved and there are some initialization vectors, and in fact the numbers are getting juggled around to build those properties that we previously talked about. That's what the constructions are. And those constructions are the one which are proven, which is going through those NIST competition and then selected that, okay, these are good algorithms and all that. That's what is happening. Okay. So there are constructions. I strongly recommend that you have a look if there is no session that covers to this detail. Otherwise, you have to plan a session just for that purpose because it will be too much for this session. Okay. Like say, for example, if you are talking of SHA-512, SHA-512 has 80 rounds. You take the data, you come back and you feed in the next block and then you continue. Like that, you keep continuing. On one block itself, you do this 80 rounds and then you take the next block and again do it. So that is a kind of work that happens. And when you, each time you get one hash value, feed it into the next round. And in the initial time, the very first time, you don't have a hash in that. So you use some fixed initialization vector and then continue. This is the way it is done. Any more questions here on these hash functions? In fact, I would have liked to talk a lot about these construction functions and all, but it is time purpose. Okay.
Yeah, I don't see any questions on the chat as well. If anyone has any questions about hash functions, please post it here. Otherwise, Mini, you will move on to the next topic after this.
Yeah, we can. Yeah.
Okay. Yeah. So, okay, if you feel like
whether you like me to cover any other topic, I could directly cover it here also. textbook Cryptography and Network Security by William Stallings. There are enough of textbooks that you can refer to. Just that I am familiar with, or I am comfortable reading. This is the book which I read. That's all it means. Okay. Cryptography and Network Security by William Stallings. Typical academic book. Okay. They explain all this well. William Stallings. This is the one which I have used for my learning. That is why I told it. Okay. And you can also look at the videos by Professor Parr. This one is also, this is a German professor, Professor Parr. There is a book on cryptography by that professor, and he also has his classroom lecture videos there. Other reference which I could give is the NPTEL course by a very specific course by the IIIT Bangalore professor Ashish Chowdhury. His lessons are also very easy to follow lessons, like simple way of explanation. So that would be the references which you could look at. Like these lessons are at typical undergraduate level lessons. So that would be easy. In fact, not only the hash function, those lessons also cover the basics of cryptography from other topics of symmetric, asymmetric, AES, RSA, all those are also covered there. Okay, if nothing more, let us, I hope they got the textbook name. Yeah, and let's go to this elliptical curve cryptography. Okay. Like there are two, like as I told before, the three fundamental building blocks which we need to try out. One is the hash function, another is asymmetric key cryptography, the AES, and the asymmetric key cryptography. And the elliptical curve cryptography is one of those asymmetric cryptography. Okay. So if you come to asymmetric cryptography, there are two keys. The symmetric cryptography and asymmetric cryptography, the primary difference is symmetric, both the sender and receiver uses the same key. Encryption and decryption is with the same key. Whereas if you are talking of asymmetric, you have a pair, you have a private key and a public key. You can compute the public key from the private key, but you cannot compute the private key from the public key. This is not mathematically possible. And these are typically based on some of the mathematical, which we call as intractable functions. Intractable functions means it's possible. There is a possibility. The concept exists, the algorithm exists, but they are not feasible to compute in a realistic computational time, like a number factorization, the RSA, the most popular or whatever is being used today as a asymmetric cryptography algorithm is RSA and ECC. These two are the most popular asymmetric algorithms that are used here, or in fact, these are the two algorithms that are used, RSA and ECC. RSA is based on the intractable function used in the RSA is number factorization. Say if you have two numbers, you can take and multiply and get the result. This is easier, but having the result, factorizing it to its original forms, original prime factors, that is computationally infeasible. Like if you are taking large prime numbers, that becomes like algorithm exists, but then it is not possible to finish that computation in a given time. In ECC, we do this intractable function, or that you call that as a discrete logarithm problem. The discrete logarithm problem is based on an elliptical curve discrete logarithm problem. Okay, so this is a concept of asymmetric encryption, irrespective of which algorithm you are using. So what you do is you have a private key and a public key, and the public key you make it public. Anybody can hold it. There is no secret. It is with you. There is no security, lowering the security just because the whole world knows about the public key. That's how it is meant to be. Whereas a private key, there is an owner of the private key. If I am the owner of the private key, the very fundamental assumption is the private key is kept private. It's not leaked. It's not available to anyone. It's only the owner who has the access to the private key. And how usually these private keys are protected? They are protected by what we call as hardware security modules or secure elements. As I told, the trusted platform modules. Trusted platform modules can be one kind of a secure storage of the private key. Irrespective of the environment, wherever in the world, whether it is a blockchain space or whether it is any other hardware security, or irrespective of whatever you use, ultimately the security of the private key, like how private the private key is kept, That is the that is what it gives the security. If you don't keep the private key secure, then okay, you don't have security at all, because whoever has access to the private key, they have access to all the data. You can mathematically compute everything. Okay, so that is what the fundamental building block. And how do you protect it? You protect it using secure storage, which are hardware protected secure elements. And if you are talking of hardware protected secure elements, the very basic is it is in a secure trusted execution environment and all that we call it. You call it secure trusted execution environment, secure elements, or hardware security modules, all that. You don't even have an API to come and access that key. You can only you do operations with the key. You can say you sign a data with this key, you encrypt a data with this key, you decrypt a data with this key, all that you can do, but you cannot tell, give me the key. That kind of an access is not there. And it will be internally generated using the internal random number generation or the entropy sources that are available at the chip level itself, like some of those what you call as the physically unclonable function, puff functions, and all are what is used for generating these kind of items. So internal entropy, you generate it there, you never let it go out of the secure environment. That is how private keys are kept protected. If you are breaking these premises, then there is no more security, okay, in whichever was the environment. And how it works is, it works in both the ways. So you can take your private key, you take a data, you encrypt it to the private key. If this is what happens, then you can decrypt with the public key and you can get the original data. And it works the other way also. You take your data, and if you have encrypted with the public key, you can decrypt it with the private key and get the data original. Both ways it works. Ultimately, the public key and private key, they are representation of the same data. Okay, like how the number factorization which are told, it's like the product or the individual elements, the factors. So both ways it works, and the use cases are different. If you are looking at the use cases, two ways. If you are trying to achieve confidentiality between A is sending a message to B, and if you are encrypting with this B's public key, as I mentioned before, if you are looking for confidentiality, that means the data should not be read by anybody else other than the genuine receiver. If this is what you are trying to achieve, you encrypt the data with the public key of the receiver. That means once it is encrypted with the public key of the receiver, only the holder of the private key can decrypt the data. And the holder of the private key is only B. Okay, only the receiver is holding the private key. So only they can, like if you want to send any data to me and whoever else get hold of it on the way, they should not be able to decrypt. What you can do is you can encrypt your data with my public key and give it to me. So it's only me who has the private key, and then only I can decrypt the data. That is where you guarantee confidentiality. So that is one use of the, you have more higher level constructs that you will see, but fundamentally these two are the ways in which you will use it. One is encryption with the confidentiality. Other part is the signature. There you talk about integrity and authenticity. So for that, what you do is you sign the message with the sender's private key. Integrity and authenticity means the data is not modified, and then it is as what it came out from me, and it is coming from me. It is coming from me means the holder of the private key. Like the data is coming from holder of the private key. If this is what you are trying to prove, then the sign the message with the sender's private key. So the receiver, what it does is it verifies the data. There is no confidentiality because you have your data and you attach the signature to it. And then it is only telling that it is integrity protected. The signature tells that data is correct and it is signed by me. So it comes from me. So authenticity is guaranteed. Only these two and this is the signature use case. These two are the typical uses of asymmetric key pair. Typical means the very base constructs. With this again you build up, like you can create as I told, your certificate transparency, your build up of your certificate hierarchy, like one leaf node signed by intermediate node, signed by certificate hierarchy, signed by root CA, like that you can build up certificate hierarchy. So various use cases you can build up, but this is how you use it. And now let us look at the elliptical curves cryptography. Okay, RSA, as I told, it is based on the number factorization, whereas elliptical curve, they are used, they are constructed based on elliptical curves. This one, if you are extremely interested, maybe I'll share one more reference to you. These are all coming from the, how to say, a unit length circle. A unit circle is our reference for all this. You can reach to that elliptical curve from that unit circle, which I'm not going that far, but then let us look at this, how this curves. If the moment you look at elliptical curves anywhere, you will see this kind of a curve. Okay, this is a kind of picture that you will see. It can be difference also. This curve can go up, even it can break it over here. Maybe this portion might be here, maybe this can be here, they may be together. All these are can also possible, but then if you look at internet telling elliptical curve, you will see this kind of structures. Okay. And these elliptical curves are typically cubic equations. Cubic equation means you have a term or in cube here on the right side. Okay, this x cube. So you have a cubic equation. What is the chat telling? If you can please post about the session and give a shout out. Okay, that's not a bad idea. Okay, see, these are typical cubic equations. The elliptical curves are based on cubic equation. And to the left side, you see this is on a y square. This is a square term, and the right side has this cubic term. And with this, what you will get is these curves are symmetric over this axis. Okay, the upstairs and downstairs are symmetric to each other. They are mirror images. The definition of an elliptical curve, you have an equation. This is the kind of equation, the nature of equation that you will see. There are various equations that you use when you talk about elliptical curve. Selection of the curve is important. Once again, I'll give you a NIST reference document which talks about what is the curve that you have to select, what are the recommended curve. NIST recommended curves are there. Those reference I'll give you so you can have a look. And how do you select the constants related to this? That it's all these operations happen in the prime field. So what is that prime number that you select? Based on all that only you say which is a curve. So you have an equation. So all these will come as xy points. So these are points on a graph, xy points. These are your basic working block. Like how you work in RSA, when you look at there, one number is your working primary unit. Here your points are your xy coordinates. Points on this elliptical curve are your primary working units. And a cubic equation. And along with this definition, you have an assumed 0 point that is a point at infinity. So when you look at all these definitions, this defines the curve for you. And then there are operations on the curve. So let us look at these operations on the curve. They are quite interesting. Okay. So without going too much into the detail, these elliptical curves has a property, like if you are interested at another time, not right now. Elliptical curves has a property that if you have 3 points on an elliptical curves that is lying on a straight line, you take a straight line, and if you have any 3 points of the elliptical curve on the point, they are all sum up to 0. Okay. That is a very basic on which all these operations are built on. Once you get this, you will get all the operations very clearly. So if you see this line, this blue line on top, okay, and if you have 3 points lying on it, C, P, Q, and this point, say let us call this R, okay. So your primary assumption is P plus Q plus R will give you 0, the point at infinity. Okay, so once you get this, you can define what is point addition, point multiplication, and all that. Let me clear up again my screen. With this assumption, what we can do is, how do you add 2 points? If you have point P and point Q, our basic starting point is P plus Q plus R is equal to the null value, that is O. Okay. If you cross on the third point, it will cross on the elliptical curve and curve on a third point. Once it crosses here, this is your minus P plus Q. And then you take the negative of that point is a reflection here. If you reflect here, that is a negative. The reason why you say is the third point. Let us assume that if you have a line like this, okay, a fully vertical line which crosses only on 2, we assume that the third point where it crosses is the O. Okay, the third point where it crosses is O. So you get P plus Q plus your O, the null point, equal to O. So that means it crossed at infinity. So if that is the case, we get P is equal to minus Q. So if these kind of points where it vertically, you do, where if it is vertical lines where it doesn't intersect anywhere else, then the reflection of that point is the negation of that point, that is minus Q. So if you consider all that, how do we compute P plus Q? So you take a line, the geometric representation, you cross it on the third point and you reflect it over this horizontal axis, and this is your P plus Q. Okay. That is the concept of point addition. And if you are talking of point multiplication, if you have to do multiplication of with a constant, okay, I'm not telling P into Q, a constant into point P, you keep doing it again and again. You take this point and then once again you do, say P, and there's also one thing, tangent. If you take a tangent, if it is tangential, the tangent will cross somewhere else, and then you can consider it crosses twice at the tangent. So you can say this is 2P, okay, like that also you can consider. So like this, you can do operations on the point. So you learned how we can do additions of these points in the elliptical curve. These are the very basic operations on which elliptical curve works. Should I do something? Point doubling. If you are doing a point doubling, then how do I double a point? Draw a tangent over that, and then it will cross somewhere else, and then you reflect it. Then you will get your 2P, double the point. And multiply with a constant, multiplication is repeated addition. And all these operations, like if you have gone into learning all those basics of cryptography, the linear algebra part of it, you don't do all this in your XY coordinate system as it is, but instead you do all of them in your prime field. Okay. All the operations are done in prime fields. Prime fields, you do a modular operation, modulo n. Okay. The modulo n is the prime number which we are talking. All the operations are done in modulo. It is the same. All those SHA, AES, RSA, all those operations are done in modulo so that you work in your constraint space. You don't go beyond those prime number that you are defining. Okay. So using all this addition and point multiplication. Multiplication means with a multiplication with a constant. These are the operations that you are using for the elliptical curve cryptography. It's very similar to the number factorization that we were talking about. Okay. And what else should I tell you? Okay. What is the hard problem that we are talking? Previously, we told that in the RSA, if you multiply 2 points, the number factorization is the hard problem. Here, the hard problem is, say, if you did multiplication, if you took a point and then if you multiply with a constant, and then if you get a Q in hand, if this is the case, you can compute Q from P. Multiplying, you can keep going forward and then you can do it. But then reverse calculation, you cannot determine that should be a small k. Okay, let me do that for. Like if you are given P and Q, you can't compute the k very easily. See, that is your hard problem that we are talking about. So if somebody knows, okay, if somebody knows P and if somebody knows, or if someone knows Q, there is a concept of a generator G that you are talking about. If someone knows Q, or you cannot know how many times you have multiplied it, or this key, you don't know that you cannot compute the K easily, and then do the reverse function. So you have already got a discrete logarithm problem or a hard problem, which is a one-way property very similar to the RSA that we are talking about. Based on this premise or this construct only, we are building all your elliptical curve cryptographic problems or cryptographic operations. The beauty with, in comparison to the RSA is the computational complexity is much more simpler, much more small complexity compared to what you can do with the RSA. RSA is very high computational complexity. Like this is a key that you are talking about, okay, the K. So for the key, it is just a random number. So the complexity of deriving a key for ECC is just as much as only deriving a good random number. Whereas if you are familiar with RSA, the moment you start with RSA, they will take two large prime numbers. That is the first line that you hear. So the moment you want to compute two large prime numbers from a seed value, you have to do iterate, and that could take long time. It could be minutes, or you have to reach to some kind of a large prime numbers. And every time you have to do primality check and all that in every cycle, whether the number is prime, you have to do all that. Even with all the computation optimization, they take time. Whereas when you are talking about ECCs, the key is that random number, how many times you are multiplying to reach there. See, that's all your the key which you are talking about. So key derivation is very fast. That is a good part. Even the operations that you do, the encrypt decrypt function. I'm not explaining the encrypt decrypt function. I could give some references. You can have a look. Once again, not get into too much of complicated part of it. That's the reason. Even the encrypt decrypt functions are much faster compared to the RSA function. So this is a hard problem that we are talking about in the ECC, elliptical curve. Elliptical curve, you take points, you multiply the point with a constant, you keep moving forward. You can move forward easily, but then knowing the result, coming back is not easy. How many times did you multiply and come back to the original is not easy to compute. So that becomes your hard problem, discrete logarithm problem on which ECCs are based. I hope that was a simpler explanation of what the ECC is.
Yeah, I think it was definitely much simpler than the online articles and things, because they go too deep into the mathematics, and then the whole crux of what is happening is just like missed out.
See, what I have also read through a lot of books and a lot of things before I understood this clearly, okay? But one line which I miss, everybody telling very explicitly is this sentence that if 3 points on a straight line, sum is 0. Usually there is not much of attention given to this concept in many of the online articles. And then you will struggle with what is happening with addition, multiplication. You don't get it easily. But once you get that, there is a point O, which is identity element, and then addition identity, and then 3 points are on straight line, the sum is 0. That's a mathematical property of elliptical curves. Once you get that, then everything else it will fall in place.
Hi, Minnie.
Yes.
Sorry, I just wanted to ask a question. Could you please explain how to calculate 2p graphically, especially if the point P is on the x-axis?
Let me clear up all the ink. Okay. So what is that you were telling? How do you compute 2p?
2p, especially if the point P is on the x-axis.
Point P is on the x-axis. This is the only point, right?
Yeah, this is the only point. So if you draw, what I've read is that you first draw a tangent. So if you can calculate if the line intersects, right? If a tangent line or intersects the curve, then you take the mirror image of the point of intersection. But if it is on the x-axis, the tangent never intersects the curve, then what happens?
So this is a special case. I have to recollect it. Maybe you may get an O in itself. This is 2p if you are telling. See, let us look at the points. Okay, I'm just working right now. Maybe I will have to look up and answer you. Once again, apply this concept. If 3 points on a straight line, the sum is 0. Okay. So how this worked, if you are talking, let's look at a normal point. If you are looking at a normal point, we tell that at the point of tangent, it is twice. Okay. So you consider it twice. Then it intersects somewhere. So you got 3 points on a straight line. So when the 3 points are on a straight line, the output is 0. Similarly, if you are looking at here, these two will form your, I think you may get an O if you are talking of this. Maybe you may get a null point. Because your third point is O. You don't have a third point other than O. Let me look up and confirm, but with my current intuitional reference, the third point, which when it never intersects, your third point will become your identity element. Then you will get 2p plus O is equal to O. That's what you could get. So if it is exactly here, you may get an O. I have to refer and confirm to you, but with my current reference, unless you are...
Based on your answer, so if 2p plus O is equal to O, 2p is also equal to O.
2p is also equal to O. So this could be a very special case of O. I do not know. I am not talking after referring somewhere. This could be a case. It needs to be confirmed.
So that point can never be taken as a generator for this curve.
No, there are properties which are asked for a generator, right? I don't think that you will be able to take this as your generator point.
Okay, maybe when we get to generators, you can tell us the properties.
No, I'm not even getting into that. I thought,
Okay.
should I prepare or not? But then I only told that, okay, you need a generator.
Right. So
Then I
this
generate
point will always stump me, especially in other types of curves when you have a circle and then you have another like
I would look up and tell you, but
parabola.
whatever I could think of, see, the concept is, once again, come back here. I need to refer back my textbook. Otherwise, I don't want to give you misinformation. Okay. That's why I'm holding it. See, when you look at here, when it is a tangent, you treated it twice. Here, you look at the tangent, you treated it twice. And then your third point, then say what we are telling is 2p plus this point r, they give you 0. So when you minus, they give you 0, this point. So you are reflected here, that gives you your sum. This is your 2p. But when you are exactly on this point, you don't have anywhere where it is intersecting. When it doesn't intersect anywhere, you treat that as a point at infinity, which is O. So this could possibly be, but I am not confirming. Okay. Offline.
So sorry about this. I just want to finish
No
a
problem.
thought.
It's just that I didn't look up, confirm with my mind, and come to you.
So if 2p is equal to O, then p itself could be that O point. So can we graphically say that the points at which the curve crosses the x-axis
No,
is
no, no,
actually
no, no. That is not O. No. O is an imaginary point at infinity.
Okay.
That's not the point. O is imaginary point at infinity. Let's keep it as an open question. We will clear it outside. There is a book called it's slightly a little bit difficult to read book, but if you really want to get into elliptical curves, there is a book on elliptical curves, or there is by the same book, Papdi Mitru, that book by computational complexity. That is also one book by Papdi Mitru. And on elliptical curves, there is one book by this Papdi Mitru. That's a good book which explains all this. Okay. It goes into the basic and explain, but that is meant for a hobby reading rather than getting here. This specific points, let me look back and then confirm to you. Okay. It doesn't mean that, no, then this would be your origin point. That's another argument. Let me hold the argument. Okay.
Penny, could you share? Do you have any more slides to cover?
Yeah.
Oh, okay. Right. I was gonna ask you if you could share some use cases of ECC. I know that in the blockchain space, like
Usually
ECC
people use ECC.
commonly
Yeah.
used, and then even Ethereum 2.0 makes heavy use of elliptic curve
ECC.
pairs with BLS signatures. So there is a lot of use cases, but maybe you
I'll
can
come
share.
there. I'll come there. I can come there. Okay. So now that you already put there, let me give those use cases since you already brought up and we are at a break of thoughts. Okay. See, the way when I am coming from this embedded system world, there are a lot of devices where you have only very low compute, like small microcontrollers, where you don't have very fancy compute capacity. And many of these algorithms, you will have a hardware accelerator, which will be providing these kind of crypto operations. But then in the absence of all these, like say, for example, a light bulb kind of scenario, okay, these days, if you are talking of a light bulb or things which are very low on compute, or a temperature sensor, those kind of items, if you have very low on compute, and then you want the strength of cryptography, but you don't want the computational capacity, that is where people use a lot of ECC because you can encrypt and decrypt faster. I'm telling from my world of embedded system, very low compute environment, you can use ECC. And even otherwise, from RSA to ECC, the world could have moved to RSA to ECC very easily. There was no reason to stay in RSA because RSA is the key size is long and it takes time to compute and key derivation is long, all that. But then the world was already deployed in RSA. And it was a change that took time. So if you are looking at over a period of time, a whole lot of people will move to ECC. Even when you think that there isn't any special need to move to ECC, ECC is having its computational efficiency without the reduction in the security. So you are talking of today's use cases where all ECC is used. In the blockchain space, a lot of them are ECC. It's not RSA. RSA is used. RSA has got very heavily deployed from the PKI space. That is your public key cryptography, the web, the internet, the web. They got deployed with the PKI with the RSA. Because of the large deployment and the interoperability concerns, people are not moving away from PKI to from RSA to ECC. But in places where there is no such constraints, like if you are talking about a hardware, if you have to give an identity certificate to a hardware, those are usually ECC keys. Because you don't want so much of compute capacity to be spent for all that. Like if you observe carefully, in spaces where you have interoperability concerns, where the legacy systems are there, the web is there, then browsers, all those are coming in, then we talk about RSA, and people support RSA. But ECC is for like moving forward, a lot of change will move forward with the ECC. It's used in various places like website certificates, digital signatures, hardware identity certificates, even your blockchain certificates. Like you may be surprised how well it is adopted when you are looking at the embedded system space. Did I answer you, or you still have questions?
Yeah, I think this is good. If anyone has any questions or more use cases, feel free to share in the chat as well. And I think there's more.
These are your encryption decryption function, like which I didn't cover all those generator polynomials and all. See, whoever asked that question, like my very hesitation was, if I get into that generator polynomial, then I should be able to work in that prime number operation, field operations, which I thought that background I didn't assume. That was the whole reason. Okay. So if you are looking at encryption, decryption, the parameters of elliptical curve, you have that group and then you have a generating point. From that generating point only you are starting. How many times your key is this number, how many times you multiplied over the generating point is the key. Okay. If you are really trying to do encryption, what you do is you send out, you take the this generator is known to everybody. Okay. It's a parameter for whatever you are selecting. And you send out this generator polynomial, generator point multiplied with n, and then you take your message. In fact, you are masking that message with your receivers. There are multiple use cases. What I'm showing now is encryption decryption with your receivers PB. That is your public key, and then you put this K here. You take this and you send out. And once you reach to this point, this is what you already have. This is what is here. And then you multiply with your NB, that is your receiver's B value, over your KG. KG is already sent. And once you expand it, K into PB will become PB is your same as NB into G, because they have multiplied the generator point with NB. And then you subtract it with NB into KG. By then, these two will become the same, and then you will get your PM. This is how you can do your encryption decryption to send out messages. Okay. I didn't want to get into this level of detail. That's why I didn't come with all that. Maybe it might be too much. Like this point KG will act as a clue on how you are able to get it. You are sending a masked message, masked with the receiver's public key, the public portion of the known information. And then you can unmask it using the PB. The public portion is in fact the K into the generator after you have done it. Like K is a random number here. You take your key, whatever is your key, you multiply with your generator, whatever you get, that is a public portion. Okay. Public portion we already told, right? If you take one point, if you take a point and you multiply with K, and if you have the output as Q, knowing Q, you cannot find out this K. Knowing Q and P, you cannot find out the K. That is what we are talking about. So this becomes a public part. And this K is the secret that we are talking about. How many times you acted on the generator point. And how do you use it? Digital signature. Okay. ECDSA, how do you do your digital signature? This is the same concept. There is nothing so much new in your digital signature, whether you are structurally, it is the same, whether you are using the signing algorithm. I did not explain. It's there as a backup, but it may not be the best to do this. It will be going too far. The ECDSA, you were referring to that, right? So whether you are using it with the elliptical curve or whether you are using it with the RSA, conceptually the construct is the same. You take your message, you run it through your hash functions, and then you get your hash, and you encrypt the hash with your sender's private key, and then you get your signature, append the signature to the data. You send the data to the receiver. See, here is your receiver boundary. You send the data appended with the signature to the receiver. The receiver will take the signature and then they will decrypt it with the sender's public key, and then you should get to the original hash value. So independently you compute the hash value onto the message. You do it independently. Once you have independently computed, you compare them together, and if they are the same, then you know that okay, there is integrity and authenticity. Integrity means the message is not modified, you got the hash value correct. I hope the structure is familiar to you from a digital signature. Digital ECDSA signature is using elliptical curve. Okay. How do you sign and how do you verify the signature? There are specific algorithm for that elliptical curve signing and verification. I hope it will be covered in some other session, or I could give you some references here. How do you sign and how do you verify it back? Like the previous construct which we say, right? How did you send out the data? Similarly, you have a signature. The signature will have only the receiver's private key, nothing else. Okay. And the sender will verify using the sender's public key. The construct, it remains the same, irrespective of whether it is RSA or ECC. And the verification happens like this. The algorithm for verification, algorithm for signing, like you could look up and see also, or the same cryptography and network security. Does William Stalling explain? I hope that explains that. Otherwise, the elliptical curve is explained very clearly by that Professor Parr's videos, Christoph Parr. Like I'm giving references from where, when I was learning some few years ago. Okay. And now let us look at the computational efficient curve choices. Okay, this is a very important part of how do you select the curve. See, this is the document which you can refer, the NIST document, recommendations for discrete logarithm-based cryptography, elliptical curve domain parameters. This is a NIST document which talks about all that. They talk about how do you have to take the generator point, how do you select the prime number fields that you have to use. In fact, these numbers are representations of prime numbers. Okay. The highest term will be like, I think you may be knowing that prime numbers, there are a lot of prime numbers of the form 2 raised to n minus 1, like 7, 2 cube minus n 1. Okay. So there are quite a lot of prime numbers of this nature, and terms which have multiples of 2 raised to n or 2 raised to n minus 1, like that. There are terms containing multiple prime numbers, prime elements minus some constant. These kind of prime numbers are very common. And all these curves, when you select the prime numbers, you select numbers like say for example P2 521. So if you select 2 raised to 521 minus 1, you will get a prime number. Okay. Similarly, this 384, I am not able to tell from my mind. All of them has few terms with a 2 raised to something and a constant, which will give you a prime number. And as you know, shift 2 raised to n operations are only shift operations, not really multiplication operations. So you can reduce the computational complexity far higher if you are using these kind of prime numbers. That's the reason that in all these cryptographic operation and elliptical operation, when you look at that field, all these prime fields are selected based on this kind of like if you look at the P256 curve, the first term will be 2 raised to 256 plus some kind of operation, few more terms with this 2 raised to something and a constant. Okay. If you look at this, that is, you will get a prime number, and that is a field that you are defining. So if that's a reason for, and these names are given based on that prime numbers that you are selecting. 384 starts with some 2 raised to 384, and then some more terms. I'm not able to recollect from top of mind. P2, like 25519, 25519, I think, or 2516. They are all curves of this prime number type. Like the very purpose is to do faster operations because you can shift instead of doing all this multiplication. Let me see, computational efficiency. I think I already covered this because in RSA you have to go and take two large prime numbers and compute those prime numbers here. Whereas in ECC, that random number tells what is your key. And in your encrypt, decrypt, these are also efficiency much efficient compared to RSA. And if your length is increasing, if your key length is increasing, at a higher key length, the scale at which your efficiency improves is also much higher. Like RSA may be going like this, your elliptical curve, the time may be much lower, it will stay here, okay. So as you go higher, this will increase much faster. This will not increase that faster, the ECC one. So if you are looking at a higher key length, then you can look at, like I would request you to refer to some research articles on, like you can go to IEEE Explore or any kind of open access like archive or somewhere where there would be enough of articles which talks about this research on these little bit old ones, because archive, you can look at them. Is there any? I don't know. You can look at them. You will see a lot of articles which are talking about how efficient the ECC compared to RSA at higher key length, how it benefits. So when you are looking for higher strength, you get much more computational efficiency. And for references, I think I was telling about references as we were going through. This is the elliptical curve cryptography, the curve selection, what are the considerations and all that. And this is about hash functions. Okay, how do you use this? Which are the approved hash functions and all. And these documents themselves give references to where you can learn these explanations and all that. Those NIST documents are good places to understand. It may be a little bit heavy reading, but then they tell what you have to look at.
Mini, I think Ovia has a question. It's
Yeah.
in the chat.
Okay, let's look at.
Mini, maybe I can explain the question. If you can go back a couple of slides.
Yeah.
Yeah, this curve choices. Yeah, so each curve is of the cubic equation, right? Y squared
Yes,
is equal
yes.
to x cubed.
It is a cubic in X. No, the equations are different. It's not that all curves have the same equation. They have that format. That's all.
No, but when you say P256, that is the field prime that you're choosing, right? This
number
represents the field prime for
this is, yeah, the field prime. Yeah, tell me.
But so the equations also can be, even with P256,
Let me bring up
you
the
can form
document.
different.
Let me bring up the document for you. Okay, which is be much more easier to discuss. I don't have to speak from my end, no?
Is my question clear?
Hold on. Okay. I had that NIST document with me. I will look up that, okay? Because that is a reference document. Okay, this document is what I'm talking about, okay? The document called NIST 800-186 recommendations for discrete logarithm based cryptography. Let us look at some examples. They tell all those parameters also for each of those curves, okay? I guess curve choice is key length, choice of underlying field. See, there is a prime field. So these are coming from, like say P256 as an example, let's take. I got your question. I'm just trying to get you a better example, okay? Implementation of modular arithmetic. The curve parameters, that's what I'm looking at, okay?
Because for a single P256, there can be many curve equations.
Tell me again. Yeah,
Or
there
else-
can be different curve equations, but then you don't go and use any kind of permutation combination. There are standard defined reference curves and you use them. See, these are the curves which are put there. So you use any of these reference curves which are defined by them, because not all curves will give you the same kind of cryptographic strength. That's the reason that these curves are defined. You don't use permutation combination. There are these recommendations tell which ones you have to use. Okay. CP224. Okay. This is for legacy only. So there are a set of parameters which you have to use. This is a prime field value. And then this AB will tell what are the constants that you have to use for the curve. And what is the generator value. All those are put here. The generator X, generator Y. These are studied and these values are put in there.
Okay.
You don't take any permutation combination and use them. So when you say P224, all parameters are defined. It's not only the prime field value.
So there is a very common one that is used in most blockchains, which is SCCP.
Yes, yes. Again, I think it is 256 again.
It's the same P256.
Yeah, it's like there are naming, like it's almost like the same P256 that you are talking. Like there are definitions like those brain pool curves. You can look at the NIST curves, brain pool curves. They all will be looking at these values. So you should look at the values defined and then use them. Like what I was telling was these names are coming from this term. Okay, this is how these names are coming. When you say P224, the prime field definition, the highest term is this. That is why people are put. It's not like that is a rule, but that is just as a norm. That is how it is defined. Did I answer you? See, the curve definition has a lot of parameters. It's not only the P, right?
Got it. That is actually very insightful. I was always wondering how the 256 or 224 came.
See, here you see the prime number is this one. This is the prime number that you get by P 2 raised to 224 minus 2 raised to 96 plus 1. Did I answer you? I
Yeah,
hope so.
yeah. Thanks a lot. Just out of curiosity.
P384. When you call P384, this is just easy to remember numbers. That's all. Okay. See, when you say P384, the prime field is coming from 2 raised to 384 minus 2 raised to 128 minus 2 raised to 96 plus 2 raised to 32 minus 1. Now, this one, like this only you get prime number.
Got it, got it.
And
Just
the highest term is used for easy way of remembering. There is no other purpose. As much as I know, there is no other purpose in that field.
So is there these standards for RSA also?
Yes. You
And
can
also,
refer to NIST documents.
RSA has to take 2 primes, and that's how it starts, right? So,
Yes.
and the whole hard problem is about prime factorization.
Yeah, it's about prime factorization.
But
Yeah.
now, if the NIST gives you the prime numbers, then what is
No. NIST doesn't give you the prime numbers.
So how does NIST define it?
Take 2 large prime numbers. That prime numbers is the key.
Okay. So it's
That's a
whoever.
secret. NIST will only tell you the operations for the RSA. For RSA, those constants are your key.
So see, the largest known primes are like limited. You cannot take random primes, right? So,
No, if you say the RSA 2048 length prime number key, that is your key. Okay. See, when you say take 2 large prime numbers, those prime numbers form the key. So that is up to the individual key derivation. That's why when you do key derivation is finding out those 2 large prime numbers. This doesn't tell you the prime numbers because then it is the secret itself. Whereas here you can, all these are only parameters. In your elliptical curve, the key is your how many times you operated on the generator point to reach there. That is your key.
Yeah, got it.
I hope you got it now.
Yeah.
See, I would recommend you have a look at this document. This would be very clearly explaining. See, all those parameters for P384 is put here. Okay. A, B, G, X, G, Y, all are put here. So you use these values and work further. That's the way to do. Because the strength of cryptography can become good or bad based on these numbers that you are selecting. No, RSA's key derivation function is not a random number. You have to really
Are
take
your
a seed.
slides
Yes.
done, Mini?
Tell me. I didn't get your
Are your
question.
slides done? Sorry.
I guess so. Let me have a look whether there is something more I wanted to say. Key derivation, encrypt, decrypt. No,
You've
this
given
was
a
my
lot of
references.
details to all of us.
Yeah, that was my last slide. Yeah.
Okay. Okay,
Which I
great.
did
Does
not
anyone
cover
else?
further. I added something. How do you do your ECDSA signature and a signature verification, which I didn't intend to cover. I think that will be too much.
Oh, okay. You've already given a lot of references that everyone has to go over. Once this recording is up, I think all of you have to go over the entire recording
Yeah,
and
I
find.
think you will have to read it once again
You
and
have
then
to
look up
find
the
these
correct references. Yeah.
Yeah. Does
Uh,
anyone
uh,
else have any last questions for?
There was one unanswered question, which I think I should update you separately.
Okay, yeah. How can they reach you, Mini, in case they have
You
any
can see me on LinkedIn.
LinkedIn? Yeah.
Yeah.
I'm just going to put this on the chat again, but please go on LinkedIn and give a shout out to Mini because her session was amazing. A lot of references for you guys.
No, the thing is, I was slightly confused starting because to what level of depth should I go? That's one.
No, but I'm sure a lot of people like Gyan and Ovia for sure would have enjoyed this session a lot, and they'll have a lot of questions, which I'm sure they'll speak to you privately and ask for more questions as well. And I'm sure there are others as well. So I think this is now up to them to read through all
I
of the
have pasted my number
link.
there.
Oh, number. Okay.
Not my number, my LinkedIn profile there.
Yeah.
Okay.
Yeah. Also, Mini, we're doing this thing where every session we're giving our cohort a small homework that they can complete. And
Okay.
it's something like write a small paragraph on what they learned today or some specific topic that they can do. Is there anything that you would like to give?
I think I should think and give you, no?
Yeah, okay, that's fine. You can give it to them later. I'll send it
How
across.
much of time they are willing to spend on the assignment?
No, not too much, I guess.
Yeah, just a small one. Like
Yeah, just a small
so
one.
far we have told like some kind of research homework, like learn
Yeah.
about this topic and write a small article or
Okay, why not we ask to write some LinkedIn articles on specific topics? Maybe I
yeah,
could give a list of topics. Any of you can pick up anyone which you find interesting and do.
Yes,
sure.
would be great. I'll contact you later and then you can give me a small homework that I can share with the cohort.
That would be good enough. Why only one homework? Give some bundle of homework. Do some research, publish it.
Okay, yeah, I'll do that.
Yeah.
There's also Maheen on this call who's been he's not on the call anymore, sorry. But Maheen's been updating everybody with resources, so you can check his resource. I'm sure he's collected all of the references and put on his Notion document already.
Okay.
So you can refer to that as well.
In fact, when I put this reference document, I didn't put large, I put 2 documents which will further refer you to the right places.
Okay. Yeah, this is anyway getting recorded. So anybody who's checking the session recording later will get all of these information.
I hope it was useful. At least I don't think that I would have been able to make all these so thorough in your mind, but at least you will know where you can look up next and learn details further.
Yeah, for sure. I guess that's it. I don't think there are any more questions. But thank you so much, Mini, for your time. The session was really insightful.
Yeah, thank you so
Thank
much
you.
Moni, for your time and for these slides as well. I know that because of your work, these slides might be confidential, but
I may not want to share the slide, but recording is fine.
yeah. So we can share the recording with everyone, right?
Yeah, because there's nothing confidential, but usually I don't have a habit of sharing slide.
Sure, sure. Yeah. We'll share the recording, no problem.
Yeah.
And
Yeah,
I
the
think we
recording
can
is
find the references from there as well.
Right. Thank you so much. I'll be sending out the email with the recordings and resources, so all of you can look at that later.
Yeah, but I would also suggest that if you are really getting into cryptography, learn it from some academic book. That is what is the easiest to learn, because you also have to learn that fundamentals of discrete logarithm problems and those prime operations, fields and rings and those group theory. Then all these are very clear. So if the interest is to learn the maths behind the cryptography, uh, get these concepts and then get back to that basics little more.
Right. Thank you again, Minnie.
Yeah, thank you. Thanks so much. And thanks for the
Thank
time.
you for the great session. Yeah. Thank you for your time. And if there are any other questions, Vinny, I'll reach out to you on WhatsApp. Like, I think people may also send like LinkedIn requests and things, but if I get any questions, I'll definitely share it with you.
Yeah. And if
Okay.
any of you have any questions that you'd like for us to send to Minnie, please put it on the WhatsApp group.
Yeah, anything is okay. Like the thing is, don't expect immediate answer. One is like before confirming, I may not want to answer you and misguide you. That is one. Another thing is time. Okay.
Yeah, thank you so much. We will, whoever wants to approach Minnie, you can just send it via her LinkedIn. And if you're able, if you have the time, then please, yeah. Thanks. Thank you, everyone.
Yeah. Bye bye. Bye bye.
Thanks, everyone.